Welcome to our presentation on rough stochastic volatility calibration. Our vision is to utilize the accurate but slow rough Bergomi stochastic volatility model in an efficient manner to predict the dynamics of tradable assets, which in our case take the form of stocks. This task is daunting because rough Bergomi model only utilizes 6 real numbers as parameters in representing these dynamics, where the factors that affect the market of an asset are essentially infinite, ranging from the metal that is harvested to produce a product to the tweets of celebrities. And we have found ourselves left with a system that to find these 6 real numbers in under 1 minute, fitting the market with an average error of 0.898%.
Diving into our model of choice, the rough Bergomi model arose from the observations of Jim Gatherell and Matthew Rosenbaum that volatility of assets is inherently rough. Technically, this means that realized volatility is driven by a fractional Brownian motion, a superset of Brownian motion that allows it to retain a sort of memory, with the Hurst index less than 0.5. But intuitively, this means that volatility is bumpy, similar to sandpaper. Here we see the coupled set of stochastic differential equations that define the rough Bergomi model. Addressing the primary limiting factor of the rough Bergomi model, its speed, we designed a neural network to approximate its solution at a significantly faster rate. However, this neural network required training, and this training requires a large amount of synthetic data. Thus, we turned to the issue of generating the synthetic data. Since the rough Bergomi model lacks an analytical solution, our only option was to utilize numerical methods. We used Monte Carlo simulations involving millions of calculations to do so, leaving us with an accurate approximation of the solution to the model.
Finally, in calibrating our network to obtain our parameters, we utilized the differential evolution method. This choice arose after experimentation with another method, including one based off gradient descent. We found that no matter the choice of initial parameters, gradient descent method kept running into troublesome local minima, not reflective of the perfect parameters to represent an asset. To train our neural network, we needed a massive dataset of synthetic data from the rough Bergomi process. The rough Bergomi process requires a massive number of Monte Carlo simulations. Our initial implementation took about 15 hours to generate the dataset. In a 36-hour datathon, waiting this long wasn't an option. We needed a way to drastically speed up the process, so we started to look for solutions. We explored multiple optimization techniques, including the parallel processing, hardware acceleration, and algorithmic improvements. After testing different approaches, we found that vectorization was the key to make our simulation significantly faster. This allowed us to complete data generation in a feasible time frame, but then we encountered a new problem. After optimizing the computation speed, we faced another serious issue, which is memory overhead. The generated data was consuming nearly 30 gigabytes of the memory, making it inefficient and impractical for our system to handle. To tackle this, we optimized two key factors, which is the number of the threads used, adjusting the thread allocation to balance the parallel processing without excessive memory usage. The batch size of the generated data. Instead of generating all the data all at once, we broke it into the smaller, manageable chunks. By carefully tuning these parameters, we successfully reduced memory consumption while maintaining fast data generation.
Finally, right here we have some of our results. This image dictates the NNIV surface, which is the neural network's generated IV surface, versus the rough Bergomi IV surface, and the residuals. As you can see, the residuals are essentially minimal at all but low maturity points. Overall, we found that our neural network approximated the rough Bergomi function very, very well. Here we have our market surface, which was pulled from Microsoft option data, and our neural network calibrated IV surface after obtaining our 6 calibrated parameters. Again, we see that the residuals are within 0 to a couple percent. This, being a very accurate prediction of the market, is a result that we are very proud of.